Good day, guys. So now we'll be talking about volumetric analysis. As you all know, volumetric analysis is also titration. And titration, let me just briefly explain what titration is. Titration is like titrating, titrating an acid rather, the base. You put an acid or another type of solution, another type of solution. When you titrate them together against each other, that's what titration is all about. And during titration, you put your base from your pipette. Your pipette usually have a fixed volume. Sometimes it has a volume of 20, and sometimes that is a volume of 25. But in Nigeria, most of the pipettes they use is usually 25 cm. And always make sure that when you are doing your practical, you make sure that you write the volume of the pipette so that when we are able to mark it, they can know the volume of the pipette to use. So now, I was talking about how titration is. After you already put your acid, the base from the pipette to the beaker, you then add your indicator. After adding your indicator, you put your acid inside the burette. You make sure that you fill it up. You can either fill it up or put it in anywhere. Let me use an example. Let me draw like an illustration. Let's say this is the burette here. This is the burette. You have 0.00 here. You have 5.0 here. Make sure you fill it to around here or here. You can fill it to any other places, but just make sure that that point that you fill it to, you record it down, and that point is your initial reading. So now, as you can see here, we have 0.00 here. That means the initial reading where they fill up the burette to was 0.00, and here you have 5.0. Where the burette where they fill the acid to was 5.00. So now, how do you do the titration? After putting your base in the beaker and adding your indicator, what you now do next is you bring your beaker to this little stand. The little stand will be here like this. Then your beaker will be here, because this little stand will hold the beaker, the burette rather. You use the little stand to hold the burette. Then you put your beaker around here. Remember, your base is already in the beaker with the base and indicator. So you keep shaking this burette has like an adjust here. So for example, now make sure that when you put your acid in the burette, it's not leaking. Make sure this place is very, very tight. Then when you want to start titrating, you will now release it a little. You already know all this. I'm just like trying to explain further for you so you can understand better. Then you keep on shaking this beaker, you shake it until it finally changes color. And as you know, when you are using methyl orange, from orange it changes to pink, yeah? So immediately it changes to pink, this acid would have dropped, you are releasing it. So the result you now get at that point is what your final burette reading is. So you then record your final burette reading. As you know, when you reduce, it's going to be going down like that. Maybe you now reach like 6.50. Then you now record it and put it there. So that is that about titration. So now, when you are tabulating your results, make sure that there are like 3 steps. Make sure that you have to draw the table. After that, make sure you write all this exactly how I wrote it. And you have to put this your burette readings, then this your final readings. Make sure that you put it in cm3. Then initial readings, to make sure you put it in cm3. Then also average volume of acid it must also be in cm3. And here you can put this one as rough titer, because as you can see, the values are not concordant and you cannot use all these 3 values. So if you don't worry, in the solution I'll explain more about that. So you can use rough titer value here, then you put first titer value here, then second titer. Then if this rough is too far, like it's not concordant, like it must be at least plus or minus 0.01. So yeah, I think plus or minus 0.1 rather. So that means if this one is 16.10, at least this one should be about 0.16.00. You get? But that's not what you are using. I'm just trying to tell you that if the difference between one title value and another title value is too great, there is no concordance, you have to what? Take it out and use it as rough, because if you go and use it and you might end up not getting an accurate result. That's why you have to make sure that they are concordant and that. So now let's go to the calculation. So I'm going to read the questions to you. The question is going to be by the side of this video. So I'm going to put it at the side of the video so you can see. Let's say A is a solution of 5 grams of HNO3, that's triazonitrate acid, in 500 cm³ of solution. So we have 5 grams of HNO3 in 500 cm³ solution. Then we have B. This is A, right? Then we have B. There is a solution of sodium hydroxide with an unknown concentration. Unknown concentration. I'm just going to shorten it to make it faster. Then they tell you that put A into a burette and titrate with 20 cm³ or 25 cm³. This is what I was saying, that you have to indicate your volume, the volume of your pipette. Because here now, they say 20 or 25. And the one most of us use in Nigeria, or the one you use mostly in Nigeria, is 25 cm³. I'm sure they will have told you this in the secondary school. So, yeah, let me just move on. So, I don't need to explain the titration process, so I'll just go straight to the calculations. Yeah. So, they gave us the equation. Sometimes they will not give you the equation, so you need to balance the equation yourself, or write out the equation yourself and balance it also. But yeah, they give us the equation. So yeah, this is an example of neutralization reaction, just so you know. And so that's that. The equation is balanced. You have hydrogen here, that's 2. You have 2 hydrogen, you have nitrogen here, 1 nitrogen, you have oxygen, this 4, you have 4. Yeah, everything is balanced. So now let's just go to the question. So let's say number 1, calculate the concentration of, and it's from all your regions here. You have to calculate number 1, concentration of A, which is the acid, in mole per dm³. So we are looking for a concentration of A in mole per dm³. You can write it as this or as this. So yeah, then we have this concentration. I also say we should calculate the concentration of B, which is this base in mole per dm³. Then also we should calculate the concentration of B in grams per dm³. Yeah, and also lastly, the mass of sodium triazonitrate 5. Sodium triazonitrate 5 if 250 cm³ of sodium hydroxide were neutralized. So now, first of all here, we need to, before we can calculate the concentration of the acid in mole per dm³, we need to first of all calculate the average volume of acid used. So I was saying that these values need to be very, very concordant, need to be very, very close to each other before you can use them. So if your initial value, the first title value you have, is too far or too different from, I'm repeating this again, make sure you don't use it, just keep 2. You get pick 2. It's not compulsory you even pick this first. You can just pick first and third, you can pick second. You just make sure you put one that are close to each other so you can get a more accurate result. And always make sure that you are very, very careful when you practice. So let's leave that. And go to volume of average volume of acid. I'm shorting it. Don't shorten it like this, your wire will confuse you. So I'm just going to pick the 16.10 plus 16.1. You must follow these steps exactly as I'm doing it. Make sure you put the unit. Then if you calculate this together, you have 32.20 over 2 cm3, which will be equals to, you punch your calculator, it will still be the same thing, 16.1 cm3. So that's the average volume of acid used. So now I'm going to calculate now the concentration of A in mole per dm cube. So now, from the question here, trying to look at the question again, they said that 500 cm3 of solution A, which is HNO3. Let me just write HNO3. HNO3 produces 5 grams. It's 5 grams. Contains 5 grams rather. 5 grams. And remember, when you are calculating in dm cube, remember that 1 dm cube is equal to 1000 cm cube. So that's why we are converting to mole per dm cube. Remember, so we need to use dm cube, and that dm cube is equal to 1000 cm cube. So if 5 grams is equal to 5000 cm cube, how many grams will be 1000 cm cube? You get, so you can just do it automatically. Or the solution HNO3 will be equals to x. So let x be equals to this one divided by this 1000. Sorry, yeah, 1000 over 500 times 5 grams. Then so that will be, if you divide this by this, you already know the answer is 2 times 5 grams per dm cube. So it will equal to 10 grams per dm cube. So yeah, so to find the concentration in mole per dm cube, there is this formula you need to take note of, which is concentration in grams per dm cube will be equals to concentration in, note this formula very well please, in mole per dm cube times, sorry, this dm cube times molar mass. Trying to shorten it as much as possible. Then the concentration in grams per dm cube is 10, yeah? So 10 will be equals to, we are looking for the concentration in mole per dm cube. So I'll just put it as cm to make it shorter. Then the molar mass of HNO3, let's calculate the molar mass of HNO3. Molar mass of HNO3 will be equals to, this is HNO3 here. You have hydrogen is 1, you have nitrogen as 14, you have oxygen as 16, yeah? 16 times 3. So now if you add everything together, punch your calculator, you have 63 grams per mole. Yeah. Then you put the 63 grams per mole here. 63 grams per mole. So let's erase that. So now, if you bring this together here, CM and CM, this cancel this, you now bring this together, then you have CM is equals to 10 over 63 grams. What are we looking for? Concentration in mole per dm cube. So if you punch your calculator, you get 0.0 15873. But then you approximate it to 3 decimal places. Make sure you approximate it to 3 decimal places also. So if you approximate it to 3 decimal places, you have this mole per dm cube. So now, calculate the concentration of B in mole per dm cube. The general formula, you know, CAVA is equals to CBVB equals to NA over NB. So you have CAVA NB equals to CBVB. So now you have the concentration. What are we looking for? CBRB. So let's just make CB the subject of the formula. So that means this VBNA will just come here. VBNA. So that means CB will be equals to, what's the concentration of acid again? 0.1559 times, what's the volume of acid used? What's the volume of acid used? The average volume of acid used is equal to 16.1. Okay, now before I continue, this CB, let me just give you the quick name of the parameters. This CB is concentration of the base. This NB is number of mole of the base. Number of mole, NA is number of mole of acid. Concentration of acid is CA. Volume of acid is VA. Volume of base is VB. So now, what is CA? Concentration of the acid. That was the one we got at first. 5159 times volume of acid, the average volume of acid used, times number of mole of the base. In the reaction, in the previous reaction, everything was 1 ratio 1. So it's 1 over volume of base. Volume of base was 25 cm3, as I said before, the general stuff. Then times 1. If you punch your calculator quickly, you are going to get 0.01023. We should just remember, okay, in this case, make it 4 decimal places, because you can't make it 0.01 again. So it has to be 4 decimal places. So then you make it 0.0102. Then mole per dm cube. So now let's go to the concentration of gas. Calculate concentration of B in gram per dm cube. Remember that formula here? Concentration in gram per dm cube is equals to molar mass times concentration on mole per dm cube. So now the concentration in gram per dm cube of this one will be equals to the molar mass of sodium hydroxide. We have sodium mass 23 plus, we have oxygen at 16, then we have, so that's what's yeah. So sodium is 23, molar mass of sodium is 23, molar mass of oxygen is 16, molar mass of hydrogen is 1. So when you add them together, you get 40. So this is 40 gram per dm cube. Now going to the next question, which is very, very complex. You have to be very careful. Of course.